Okay, let's talk about molecular orbital theory. The first thing we need to discuss is the interaction of waves, because at the core of it all, molecular orbital theory is all about waves in the context of electrons interacting with nuclei. Now, one thing to be aware of is that when you have two waves coming in contact with each other, if they do so in phase with each other, meaning that crests line up with crests and troughs line up with troughs, you end up creating a wave that is got greater amplitude. But when the waves are actually out of phase with each other, when they come in contact with one another, they actually end up canceling each other's out in terms of the amplitude, and you have a destructive interference. Now, the orbitals themselves behave very much in this fashion. They are technically wave interactions of the electron with the nucleus. But you could bring them together in phase, meaning that the shading of the two orbitals would be the same. So you could have two s orbitals coming together to give you this oval shape. Or you could have the p orbital coming head-on with the s orbital of the same shading to give you an oval region. Or you could even have d orbitals doing this thing, or two p orbitals or two d orbitals of the same shading to give you this overall oval cylindrical region of bonding space. We call that the sigma bond. And another thing to be of notice is that there is no nodes present in this bond. This is a bonding interaction through and through. But if you were actually bringing the orbitals together such that they would be out of phase, and you depict the out of phase aspect of the orbitals by having the different shades on them, so you could have the unshaded s orbital mixing with a shaded s orbital, you will basically create a destructive interference event in which you create a node right where the bond should be present. And this could happen with s orbital with head-on p orbital, or head-on d orbital s orbital, or two head-on p orbitals, or two head-on d orbitals. As long as the shading is opposite on each of them, then you're going to have these nodes right through the vertical axis of where the bond should be. And notice that we also depict this bond as a sigma bond, but we specifically call it a sigma star bond, with the star denominating the fact that we have a node right in between where the actual bonding interaction should be. A similar story takes place with the p orbitals. If you bring them side to side, you get your pi bond or your donut. If you have a d orbital coming head-on with a p orbital, you get a donut as well. And if you have two d orbitals, you could also make another donut right in the middle. Now the pi bond right here is fully constructive. You actually have a good interaction. There's no disruptions in the actual bond that you created. But if you were to bring the p orbitals out of phase with each other, meaning that upper portion is shaded, lower portion is shaded on the other one, the moment you bring them together, you create an anti-bond right in the vertical axis. And like the sigma bonds, anti-bonds are depicted with the star symbol. So a pi star will tell you that you have a pi orbital that happens to be anti-bonding and has a node right in the middle. Alright, so now let's talk about the rules of molecular orbital theory before we start doing some examples. Okay, so first rule. The orbitals have to have the same symmetry. If you bring orbitals of that are basically head-on, right, like this p orbital and that d orbital, you can create your sigma orbital no problem. And you could even do so even with different shading. Having same shading or different shading is not the same as saying that they don't have the same symmetry. This will create a sigma bond in one instance bonding and the other instance anti-bonding. But what you're not allowed to do is to bring a p orbital with an s orbital such that they are head-on. Because if you do that, you end up creating a situation in which part of this orbital is bonding, but the other portion of equal size is anti-bonding. And basically those two things completely annul each other. Same thing can be said here for you, the orbital. If you bring a head-on p orbital with it, you'll create the same type of nonsense. Some part of it will be anti-bonding, some part of it will be bonding, and overall you have no bonds. So make sure that this is of the same symmetry. Head-on with head-on or side-on with side-on. Alright, now the other thing is that you have also separations. Right now, notice this. This particular graph is showing you that there is some energy separation for the 1s orbitals, shown here in red, the 2s, and the 2p. And the ones that are, lowering energy tell you that you have more stability with those orbitals. And generally speaking, you want orbitals of roughly the same energy to interact with one another. So we're going to make use of that once we start drawing the diagrams. The last feature is that whatever number of atomic orbitals you start with is the same number of molecular orbitals that you're going to generate. Alright, now one last thing, and this is actually the most hand-wavy part of the entire process. I'm going to give you a means to roughly get an idea of how to draw these diagrams in a pseudo-scale, so to say. I personally like to look at Rydbergs in terms of the energy of the actual plots right here for the 1s, the 2s, and 2p. And if you focus solely on those ones and kind of get rid of the 1s for elements on the second row, because those energies are way down there, they're basically core electrons. Basically you get a relatively decent view of where the actual orbital energies are going to be. So and these are all in Rydbergs right here. So you go from 0 Rydbergs down to -4 Rydbergs. So the farther down you go, the more stable you are. And here I'm going to zoom in a little bit more. You'll notice that right at the beginning of the second row, there's actually very small separation of energy between the s and the p orbitals. But as you keep going farther and farther to the right, the separation gets bigger, bigger, and bigger. This is going to have some consequences for how we draw ultimately the orbitals. Alright, so I'm going to stop the video right here, and on the next video I'm going to derive for you the molecular orbital diagrams for diatomic molecules involving elements starting from lithium up until nitrogen, and then I'll show you the derivation for the molecular orbitals of elements containing oxygen up until neon.